Hi class. So back to part two now, electric boogaloo of counting and probability. So we have just a couple more rules to talk about. And again, it's really helpful that we have done sets before because that's kind of how we're going to write out some of these formulas. And they're kind of simple ideas, and we can also draw some Venn diagrams to help us. And again, we want to learn in this section how to count these things, and then also, of course, how to calculate probability on those as well. So the first idea is that we have the addition rule. Now, what this says is that it's kind of very particular. It says that we need to have distinct mutually disjoint. Remember what that means? That just means no shared elements. So in other words, we say A1 intersect A2 is empty. Remember, that's what disjoint means, mutually disjoint. So obviously, if they share no elements, and we were saying that A equals, the union of all of these sets here, A3 union dot 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 union up to A sub K, then if I want to talk about the number of A, well, it would just be the number of that, right? A2 union A3 union dot 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 union A sub K. Well, what this theorem says is that basically if we have this, if I even say AI and AJ for all I doesn't equal J, so all pairs of these sets are mutually disjoint, then the number of this is kind of like you can just distribute the number thing, okay, and just count them all. And that's what it's saying. A1 plus the number of A2 plus the number of A3 plus dot 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 all the way up to the kth uh, little subset there. Okay. All right. Now this only works when, again, they're mutually disjoint. Okay. We're going to talk about the case when they're not mutually disjoint in a second. But let's go over here. So here's an example. How many three-digit integers are, so between here and here, are divisible by 5? Okay. All right, well, let's take a look. There's only two ways you can be divisible by 5. Your last digit is either 0 uh, or your last digit is 5, lands in 5. As an example, 10 is divisible by 5. That's cool. 15 is divisible by 5. That's cool. And it doesn't work any other way. Okay? And if we're doing three-digit numbers, I could say, 110 and 115. Okay. Well, that's wrong. Now it's 22 and this is 23. Okay. So we can use this kind of idea to say, all right, well, there's two ways I'm divisible by 5. My last digit ends in 0 or my last digit ends in 5. And luckily, there's no common ground. If your last digit is 0, your last digit is not 5. So we can call this bucket, A1, and we can call this bucket A2. And the fact or the helpful fact is that, A1 intersect A2 is empty. There's no number that has, 0 and 5 uh, as its last digit. So that's nice. So then we can go ahead and just calculate that. Now, how do we do that? Well, three digit, that end in 0 or so let's talk about the ending in 0 part. So A1 was the 0 endings, okay? If I'm a three-digit integer, okay, that means I have two choices for my other ones. So my first box, I can have 9 choices. I can be 900 or I can be 800 or 700, blah, 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 even down to 100. And so I have 9 choices here, okay? And then how many choices do I have for my middle number? Well, my middle number I actually have 10 choices, right? Because it's not just 1 through 9, but I can include 0 because 0 is a placeholder. So 905, for instance, okay? Or excuse me, 910, to end in 0. So I actually have 10 choices here. And then here we're saying, okay, boom, you're sticking, the number here ends in 0. Luckily, this is just going to be the multiplication rule, right? Because, these are the two ways it can happen, N1 and N2A, and then you just multiply them. So this, I get 90 of them. So the n of A1 is 90. And for same thing for A2, if I'm ending in 5, there's only one way to do that. Ends in 5. Okay, but the middle number can be, there's 10 of them. There's 10 ways, there's one way. And then, because this can be 0, 1, 2, dot, 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 up to 9. And these have to be 1, 2, 3, dot, 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 up to 9. So there's 9 ways here. So this is also going to be 9 times 10, which is 90. All right. And so the way we calculate then what we wanted, so the number of 3-digit integers that are divisible by 5, it's just going to be according to the addition rule, just that plus that. And so that's going to be 90 plus 90, which is 180. There you go. And again, the key thing there was, the fact there was that A1 intersect A2 was empty. Sorry, was empty. There was no common thing there. And that allows us to use the addition rule. Okay. We can't use the addition rule otherwise, or the theorem. All right, so excuse me, let's talk about the difference rule. So there's another rule that we can use, which is that if we say we have a different number of sets say we're trying to calculate the number of things in a finite set A, and we have a subset. So again, here we have B as a subset of A. So imagine we have A and B lives inside of it. So this is B and this is A and some universe that we have here. So when we're trying to calculate the number of A minus B, so what would that look like? Well, in a different color, we would want all the things that are in A that are not in B. Well, that would just be this, right? It's starting to look like a cell in biology, isn't it? That's the nucleus, B is the nucleus, and we have the cytoplasm here. Well, anyways, so this theorem says, makes sense. If B is completely inside of A, then if I'm trying to find the difference, it should just be the number in A, take away the number in B. And that's all this says. Okay, pretty straightforward. The key thing there is that, the hypothesis is that A has to be finite. This doesn't work for infinite sets. And B is completely inside of A. It's a subset of A. So let's, do some more examples here to try to make it clearer. So for part A, so we have talking about pins again. And same deal as we did in a previous video, 26 letters and 10 digits. So, that means there's 36 possible things, 26 plus 10. We actually calculated these in a previous video, there are 1 million, blah, 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 for repetition allowed, and 1,400,000, blah, 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 if you don't allow a repeated symbol. So part A is asking how many pins contain at least one repeated symbol. Well, if you think about it, one repeated symbol, okay, means that you can think of this as like, let's call this set B here, and you can call this set A. Now, if I want at least one repeated symbol, that would just be B minus A, right? Because, again, in our universe, B is all make sure I'm using sorry, I should use the other notation here, A here. And that's B. In the theorem, they said B was a subset. So here, this is repetition allowed. Okay. And A, actually, this doesn't make sense. Let me just do it a different way. Okay. That picture I was drawing was incorrect, so I apologize about that. Well, so for part A, if we want to say, let's say that S is the set of all the pins with repetition allowed, so we just call it S. Sorry, I should use the notation that they have up here. Anyways, so let's call that S here, okay, and then we can call this A, okay. So A here is no repeated symbols. whereas S is repetition is allowed. So if I want at least one, that just means that it's going to be the difference between them because A is no repeats and S is repeats. So to live in here, I'm allowed to live in S, but not in A. That's what I was trying to say earlier. Sorry, with the subsets and all that stuff. So this we can call it as S minus A. It's in the subset of S where repetition is allowed, but I'm excluding the ones where there's no repeated symbol. So I actually had it right with the Venn diagram. Sorry. Well, anyways, so for part A, actually, sorry, I have more stuff here. Again, we call S the set of that, and A no repeated. Okay, so that means it's just going to be N S minus A is N S minus A. Now, this is a fact, that S intersect A was empty, kind of by definition. S was repetition was allowed, okay, but actually that's not true. Forget that. Okay, I was thinking about the addition rule. Okay, never mind. Sorry. A is a subset of S. So anyways, because A is a subset of S, uh, we can use the difference rule or difference law rule. Okay. And so N S minus A is just going to be that. And so then we just plug it in and we have N 1,679,000, blah, blah, blah. Sorry, I had two different the two different theorems mixed up in my head for a second. So I was messing up. But anyways, here we go. 265,896. Hopefully I did that correct earlier on a calculator, but check me if I'm wrong. Okay, cool. Yes, so this was, sorry, we have that universal thing. S is all the pins, so repetition is allowed, but A is a strict subset where I'm not allowed any repetitions. And so obviously what we're looking for, if I have at least one repetition, I'm not in A, but I'm in S. So that's that one. So that's why we're unable to do the difference rule, difference law. Okay. So part B asks, sorry, I should have wrote the question down again. Part B asks, if all pins are equally likely, what is the probability that a randomly chosen pin contains at least one? Well, this again, if we call that E, or actually S minus A, I should say. Um, and that, what we're really looking for is the probability of S minus A. Well, the key word there is it says that these are all equally likely. So we can do the naive probability rule, which says that, okay, that's going to just be the probability of S minus A. Sorry, the number of S minus A all over the number of S. Okay, because S is the total sample space. And I can write that again over here for B. Okay, this is going to be the number. So probability of S minus A is the number of S minus A all over the number of the sample space, which is going to be the answer we found before, 265,896, divided by the total big number, sample space number. Okay, and that's roughly equal to 0.158, roughly equal to 15.8%. Okay, so not a lot actually, it's lower than I thought it would be, less than 1/6 have a repeated symbol. All right, moving on here. I'm going to come back to this formula when we do a problem, but what it says is that also we have a really handy dandy formula when we're trying to find the probability of a complement. Remember what complement means? A complement means, so a complement is defined as this, all the things that are not in A, but in the universe. So here our universe is typically going to be S, the sample space. So it would just be S minus A, typically, where S is the sample space. Okay. So to live in the complement, I have to live in the sample space, but not in A. So what this is saying is that the probability of A complement is just the probability of S minus A, which is just probability of 1 minus the probability of A. Now, this is actually just an application of the difference rule because the probability of the sample space is 1 by definition. The sample space is everything. So here we get here. Now, an important corollary for this, and you might want to write it down, corollary, is that when I want to say the probability of at least 1, well, what's the complement of at least 1? has to be zero, right? Because at least one means one, two, three, four, five, so etc. So that means that the complement of at least one would be zero, and so it would be one minus probability of zero, or say one minus probability of none. Okay, because the complement of at least one is none. Okay, so that's cool. That's a cool corollary. Actually, should go over everything. Let me write that here. Probability of at least one, okay, is one minus the probability. Cool. We're gonna use that in a second. So here we go for more passwords. Okay, so here we have this. It says a certain computer. Okay, so again, here we're only having 3 through 5 uppercase letters. Okay, so that's 26 total possible. Uh, 26 in the Roman alphabet. Okay, and we're not saying that we're allowed to have numbers for this problem. Okay, so that's cool. Makes it a little bit easier. So part A asks, how many different passwords are possible? Okay, obviously there's a terrible password system. There's only 3, 4, or 5 length. Okay, so this is like even worse than most pins. But anyways, let's imagine that this is what's happening here. This is why on the computer, on when you sign up for stuff, they usually want it to be 8 to 10 to 12 to whatever length, because this is a really small sample space, as we're going to find out. So how many different passwords are possible? Okay, well, the set of all passwords, they told us that a password either has length 3, 4, 5, so we can set this up into a partition and say, okay, well, we have uh, these three possible things. Okay. Now the key thing is that A1 intersect A2 is empty, A1 intersect A3 is empty, and same thing for A2, A3 is empty, obviously, right? Because you can't have length 3 and length 4. Okay, did I leave enough room? Okay, so I'm gonna have to do the answer here. All right, so let's do A1 and A2 and A3. So A1 here, well, how many passwords do I have? Well, I have, three letters, right? Three parts of the password, and I have how many choices? I have 26, so it's just going to be 26, 26, 26. So using the multiplication rule, this is just going to be 26 cubed. Okay, and I have that here, or I think maybe I just left it. Yeah, I just left it. Okay, for A2, same deal. Is, I have 4 choices, and in each choice, I have 26 letters to choose from. And so it's just going to be 26 to the fourth and yada, yada. A3, get the idea, 26 to the 5, because I have 5 parts to the pin and I have 26 choices in each one. Again, this is just using that multiplication rule that we learned last time. Okay, so now if we want to figure out so let's call A this whole set, these unions here, then we know that it's just going to be the n of A is just going to be the number of them, just is this union A2, A3. According to the addition rule, or the theorem, this is just equal to A1 plus NA2 plus NA3. All right, well, then we just add them up. And again, the key thing here is that they were mutually disjoint. We couldn't use that theorem otherwise. All right, and then you just add them up. 26 cubed plus 26 to the fourth plus 26 to the 5. I did write that down. It's going to equal 12,355,928. Now, I said earlier on the video, oh, that's a really small sample space. That is a really small sample space for a password, okay? Because hackers can crack a password. They can do hundreds of millions in a minute. They can try 100 million passwords in a minute. So that's very small. All right, part B. How many different passwords have no repeated letter? So again, we can separate it out into the three spots. We have A1, A2, A3. These are three letter passwords. You get the idea. 5 letter passwords and 4 letter passwords. All that really matters is, how do we change it? And obviously A is just going to equal the union of that, blah, blah, blah. Okay. So how do we calculate a number of A1 and A2 and A3? Well, let's think about it. So number for A1 here. Well, I have three letters in my password. Now they're saying the only difference about here is that I can't repeat. So how many choices do I have for the first one? Well, I have 26 choices for the first one, but once I've chosen a letter like Z, I can't have Z again. So that means I only have 25 choices for the second one. And then of course I only have 24 choices because I've already done two. So this is going to be 26 times 25 times 24. And the same thing, we did this last video for this type of problems, this is why it's going down. And so here I have four things. And so it's going to be 26, 25, 24, 23. And so whatever that is. So 26, 25, 24, 23. And similarly for A3, it's just going to be, 26, run out of room here, 24, 23 times 22. Okay. For the same reason, using that multiplication rule. Okay, so obviously, the number of A here is just going to be the number of these added up. Now these are disjoint as well because, again, same reason. I can't have 3 letters and 4 letters, yada, yada. So get that. And I'm kind of running out of room here, but this ends up just equaling, this plus this plus this, which I calculated earlier, and it equals 8,268,000. Okay, so even less than before, about 4 million less than before. Okay, and this we're allowed to do from the addition rule. Again, because, these are all disjoint. A1, A2, and A3. They're all pairwise disjoint. Okay, part C asks, how many different passwords have at least one repeated letter? Okay. Well, we know from part A, that told us that the total number, right? So that was total uh, number of passwords was 12,355,928. Okay, that was up here. And B told us with repetition. Okay, sorry, without repetition. So B was without repetition. Was 8,268,000. Okay. So for C here, it would just be the difference, which would just be this minus this. So it's just 12,355,028 minus 8,268,000. That, okay, and that equals 4 million. It's just kind of obvious, right? One is with repetitions and one with no repetitions. So at least one, remember, that would be the sample space, minus the none. Okay, very cool. And again, this is because without repetition, so this answer here is a subset of here, so because B was a subset of A. The answer in B was a subset of the answer in A. So we're allowed to do the difference law. Okay. Cool. And D says if all the passwords are equally likely, okay, so now we're talking about probability here. What is the probability that a randomly chosen password has at least one repeated letter? So again, remember I talked about earlier, probability of at least one would be 1 minus the probability of none. Okay. Uh, for this one, it probably would be easier. So part B told us that the probability of none, or they told us none. So remember the number of no repeats, okay, was 8,268,000. Okay. So the probability of no repeats, this is from part B, you know. So the probability of no repeats, well, that would just be the number of no repeats divided by the number of the sample space. So all passwords. Okay, so that would be 8,268,000 divided by, what was it, 14 million, I forgot already. Sorry, 12 million, 355,928. Okay. So to answer this question, sorry, I ran out of room here. So to answer this, we could just use this formula. Okay. The probability of at least one is one minus probability of none. Okay. We could say, okay, that's going to equal one minus this ugly fraction, 268,000, 12,355,928. Okay. Whatever that is. I don't really care so much about the decimal answer. I did calculate it earlier. So this roughly equals um, about 33%. 33%. Okay. All right, cool. That's one way to do the problem. You could also do this problem by just taking the answer from part C right here and then dividing by the answer from part A. So it's the exact same answer. Okay. So another method would just be take the answer from C and divide by the answer from A, because this was none. Um, uh, this was, yeah, none. Yeah. Well, anyways, you don't have to do it that way. But yes, this is the same answer if you do C divided by D, because it's just going to be that number, which was have at least one repeated letter, okay, which is what it's asking for. Yeah. So you could just take the answer from C, which is 4 million roughly, and divide it by the total sample space, and you get the same answer. I just wanted to show you there's two ways to do it. Yes. And so just remember that the key here, key takeaway or corollary, is probability of at least one is one minus the probability of none. Again, because the complement of at least one is none. So that's why. All right, we are doing really well here. You guys are sticking with it. Okay, we're getting to the last major idea from this section, which is called the inclusion-exclusion rule. Okay. What this says is that say we have, so in the previous theorem for the addition rule, we said that there was no overlap. Okay, so back we said that this intersection had to be empty. But the question obviously is, what if, A intersect B doesn't isn't the empty set? So other words, there's overlap. So what if there's overlap between A and B? Can we still come up with a formula to add A and B? And yes, that's what this exclusion rule says. Okay. It says, say you have finite sets, A, B, and C. Okay. Then the number of A and B. Okay. Let's do the the two set rule first. Okay. So this is just two sets here. The number of A and B is, you can add like the naive, the addition rule from before. You can just add them. Okay. But what does it say? It says, oh, snap, you need to take away the intersection. Now, why the heck is that? So let's go back to the picture here. We have some universe. We have A. We have B. Okay. And we have some A here, we have some B here, and then we have some, some intersection. So why the heck is this theorem working out the way it is? That the number of A union B is you take the number of A, you take the number of B, but then you take away the middle. Well, think about it. If I added the number of A here, let me draw in red here, that would include this little middle section, right? So that includes that as well. Okay, so the number of A has the yellow part already. So that would be like blue plus yellow. Let me draw that in a different color here. Okay. Now the number of B here has the green plus the yellow as well. Let me get rid of the red here. This doesn't help. Anyways, like that. Supposed to have yellow. Okay. So what would happen if I didn't have this theorem here? If I just went to naively add A plus B, okay, that would be blue plus yellow plus green plus yellow. Oh, snap. I have yellow twice. Not good. Okay. So what I better need to do, if I went to go add this, because there's this intersection, this non-empty intersection, to get this an accurate count, I have to actually take away a yellow. Okay. Because I overcounted. Right now I have counted it twice. So I've counted yellow twice. So the way we get around it in this formula is that if there is intersection, if they have this overlap, this is like taking away the yellow. So we just want to take away that yellow once so that we don't double count it. And then we would just be counting it just this. And so we would have that, which is good. And it's the same thing for three sets. Okay. It just all you have to worry about is you add up all the sets, but then you take away the intersection each time. Like that. Okay. And then you take away the overall intersection. Okay, so it's gonna be 4 intersections. But all these are just the intersections. All the intersections that we double counted. Excuse me. These 3 that we double counted. All right. And because we took away all the double counts, we actually ended up taking away 1 too many. And so we need to add back the like the center where they're all intersected. It's hard to draw that for 3 sets, but for 3 sets, it's kind of like this. You have A, you have B, and you have C. Kind of like the Olympics, or a tray. It's called a trefoil, a trifoil, something like that. So, anyways, this little intersection right here in the very middle, that part is right here. Okay. Anyways, you can just, if you don't want to think about it, you can always just, look back on the theorem or whatever. But let's take a look at an example here. So how many integers from 1 through 1,000 are multiples of 3 or 5? Okay. And then we'll do part B as well. Okay, so part A asks, again, say we're going through 1 through 1,000, 3, 4, 5, ... Okay. How many of them are going to be multiples of 3 or a multiple of 5? Well, let's say A is a set of your multiple of 3, and let's say A, you're a multiple of 5. Okay. So the union would include the or, right? So that would be the multiples of 3 or the multiples of 5. Okay. Now, what's the problem? Well, I could also be divisible by both, right? Both 3 and 5. So that's what the intersection is talking about. So 3 and 5, that would mean I'd be divisible by 3 and 5. That means I'm divisible by 15 by 3 times 5, which is 15. So basically, I need to kind of remove those. So what the theorem says is that, okay, well, you need to figure out what the number of A is. So just remember what the theorem says. The number of A union B is the number of A plus the number of B minus the intersection, sorry, not union. Okay, so all I can do is I can just kind of build it up. So I kind of drew it out ahead of time to save some time, but if you think about how many are going to be multiples of three, well, you can start counting them out, you know, one, two, three, six, blah, blah, blah. Anyways, really what you can do is you can just take 1000 and divide by three, and you get the and take the nearest the lower or whole number, okay, or just count to 99. 99 divided by three is 333. So there are 333 on this list. So n of a would equal 333. And same thing if you do fives, it has to be a multiple of k, okay? And same deal, take that last number, divide by five. That goes into it completely, and so you get 200. So you get n of b is 200. But now we have to ask ourselves, okay, oh snap, what about the intersection of A and B? Well, again, like I said, 3 times 5 is 15, okay? You go up as far as you can, you know, the last one you get up to is 990. You could just take 1000 and divide by 15, and you would get 66 and 2/3. So round down to the lowest number, 66, and that tells you how many go into it completely. And so that tells us here what the number of A intersect B is. Okay, is 66. All right, I'm just kind of summarizing that there. So to finish out, that means that this, we can just start plugging and chugging. So A, we found out to be, the number of A was 333. This we found out to be 200. But then we were double counting, right? Because we had the multiples of 15. So we need to take them away. And so that was 66. Like that. Right? That's 533. And I think 533 take away 66. I think that's 467. Okay. So this was the inclusion exclusion principle, and this was the double count that we had to remove. Okay. And this is by the inclusion exclusion principle. Okay. Cool. Okay, so part B asks, okay, all right, same thing, 1000 integers, blah, blah, blah. Okay. And by part A, you know, 467 are the multiples of three or multiples of five. Okay. So obviously that means if we want to ask what's the neither the multiple of three or five, it would just be the complement, right? And so that would just be answering that question, which if you go back up to what the question was asking, sorry, I should have repeated the question. It asks how many integers are neither multiples of three, neither multiples of five. Well, that would just be the complement of, of so it'd be the complement of the answer from part A. Okay. So that's what I was just doing on the answer key here. You know, when I worked it out, okay, it would just be, well, the total sample is 1000. We figured out the answer for part A is 467. So the complement of 467 would be 533. And so that's why the answer is 533. Okay. And that is from the set difference. It's just n of s minus n of a, like that. All right. So that's all from this section. As you might have noticed, there's not a lot of proofs here in this chapter, and that's fine. So we're just going to kind of just be using set. The ideas we learned from set theory last, couple, last chapter, I think it was chapter, I can't remember offhand. It's 5, I think. Well, anyways, the set theory chapter that we did, we are just going to be using those ideas to apply. And if you want to make a flashcards or anything, remember kind of what we need are just these theorems that give us these formula on how to calculate either probability or how to calculate counting. Okay. So kind of these things in the blue boxes like that. And I would say students do typically pretty well on this chapter. It's not as much work. And also, again, like I said, there's not a whole lot of proving here. So it's just going to be kind of us working through calculating all these things. All right. I hope you have fun on the homework, and I'll see you for the next video. Thanks.